Savage on Lamello.
Hi everyone, I'm Valkyrie Savage and I'm here to present some work that I did with my collaborators both at UC Berkeley and at Adobe. So I want to talk about designing tangible input devices. Today designers use 3D printers as a part of this design process, but typically just to print a shell. After printing, designers stuff their shells full of electronics so the prototypes actually function and they can test them. The issue here, of course, is that most 3D printers only print passive materials, typically plastic. But wouldn't it be cool if those plastic pieces were functional input components? Say you print out a plastic slider input and stick it on your wall. When you slide the slider, your cell phone hears it. Communicating with your house, it can brighten your lights. Or maybe I pull the slider off the wall and use it as an input to a game. I'll show you the work that we did that goes towards such input. Some other prior work has focused on using audio as an input. They use scratching to sense identity and to input direction, but we wanted to explore using audio to sense these more tangible inputs. We want to enable rich, tangible interaction beyond scratching with a fingernail. We also want our components to be easy to use. They should be functional as soon as they come out of the printer and not require assembly. This implies that they'll be training free, that we won't have to initialize a machine learning classifier. We settled on tines as our sound generation method. So let's look at the simplest example. Here's a button. If we look at a cutaway view of the model, we see that there's a ridge around the shaft of the button that strikes the tine each time the button is pressed or released. This causes the tine to vibrate, and a contact microphone that's attached to the model can capture this vibration as a sound. This is the basic excitation of a tine that all of our components are built around. Smaller tines vibrate at higher frequencies and longer tines vibrate at lower frequencies. We integrated tines into 4 different kinds of traditional input components: buttons, as I showed, direction pads, dials, and sliders. Direction pads have 4 tines, which are struck when the user moves the stick up, down, left, or right. Dials have a small striker on the shaft that's pulled past tines that are arranged radially. And sliders, of course, have a striker that's pulled past tines arranged linearly. So we'll go into the details of the system. Lamello is a sensing technique that requires no training or initialization, just the digital model as an input. Sensing is done via passive audio. You clip a contact mic onto the device for sensing. And using the object's digital geometry, our software parses the sound and turns it into high-level interaction events. So how do we get frequencies from a 3D model? We model our tines as tiny cantilevered beams. In particular, the numbers that interest us are the breadth, thickness, and length of the tines. Then there's a material component to our model. We have to know how flexible and heavy the material is, and essentially how quickly it will spring back into place. The quicker a material can spring back into place, the higher its vibrational frequency will be. In this vein, we experimented with 2 materials: 3D printed ABS plastic and laser-cut Delrin, which can be integrated into 3D printed bodies. So how exactly does a material affect the frequency? Luckily, mechanical engineering has studied the behavior of vibrational structures. They even provide us with a closed-form model of how a cantilever operates. So if we simplify this, we can clearly see our materials parameters and our model parameters coming into play. Interestingly, the breadth of the tine actually cancels out. There's one thing about the model we're using. It assumes a uniform cantilevered beam, so we weren't sure if it would hold when we use 3D printing. The way that objects are fabricated on 3D printers, they're not uniform, and each direction has a different structure. So in order to validate the model, we ran predictions on data from the digital model of a comb that we later printed. We then did the same calculations using the actual printed breadth, height, and length, which we measured with calipers. Finally, we observed, using a microphone and the complete and fabricated tines, the fundamental frequencies of those tines. As you can see, the model actually worked quite well. The materials parameters varied widely depending on how the parts were oriented in the machine, which machine we used to print, and even the color of the material that we used for printing. However, we got good results. Over all the components, the mean error was just 69 Hz and the standard deviation was 112. So now how do we get from the sound waves that we hear with the microphone into actions? Here's 2 sound waves that correspond to different tines. If we look at a spectrogram with time on the x-axis and frequency on the y-axis, we can see that their frequency spectra are different. Basically what we're seeing in these graphs is a heat map that shows which frequencies are active at which times. A brighter mark means more energy at a particular frequency. We break these signals into two parts: the transient, a broadband activation across several frequencies, and the steady state, where only a few frequencies continue in time. These are the fundamental frequencies of the tine. We see here that one tine has a higher fundamental frequency than the other. Our algorithm looks at a slice of the steady state and uses an FFT to pull out the most prominent frequencies. This classification takes about 100 milliseconds from transient to final output. Starting at the raw FFT, we can then look in the region of all the predicted frequencies to see where there's the most energy. So for this we use multiplication by Gaussians. In this case, you can see that the energy peaks around 1103 Hz, so we classify this signal as belonging to that time. Here's an example of the system working in real time. It also gives you a flavor for how loud the tines are. And here's what the microphone's hearing and what it's using to classify. The natural question, of course, is how well does this software-hardware combo actually work? We performed a few experiments on our FDM-printed and laser-cut tines, striking each 10 times and running the recordings through our classifier. We used precision and recall in as our measures. In this case, the precision for a tine T indicates what proportion of tine strikes that were classified as T really came from T, and recall indicates what proportion of T strikes were correctly classified as coming from T. In the first set of experiments we did, on a set of 7 distinct frequencies, we got precision and recall hanging around 60%, and it wasn't very encouraging, so we dug a little deeper. It turns out we have a very hard time distinguishing frequencies in the range around 2000 Hz and above. Higher frequencies decay faster and have lower energy, while you see that the lower frequencies have more energy for a longer period. Our current algorithm just doesn't have enough time to make a choice on these higher frequencies. So we went back and performed additional tests, this time ignoring the tines whose frequencies were too high. We achieved precision and recall that assured us that the area is fruitful for further examination. We also noticed that finger-plucked Delrin outperformed the FDM slider and dial. This could be due to material uniformity, since Delrin is much more uniform, or to the design of the striking mechanisms. So let me conclude with a few limitations and thoughts on future work. Creating these structures from non-uniform materials means that in certain orientations, the printed tines don't hold up well to use. They just split apart on the layer boundaries. Additionally, we want to explore robust noise cancellation. We haven't yet achieved a sensing quality high enough to fulfill the scenario I described in the beginning. While we've done some experiments with laptop microphones, contact microphones clearly have much better robustness to background noise. In any case, we showed that tines can allow for expressive input interactions with already familiar components, that the frequencies can be accurately predicted from geometry, which enables no-train classifiers, and that classification from passive audio is relatively simple and can run with good accuracy and reasonable latency. Thank you, and I'm ready to accept questions. Probably just one.
Thanks for the great talk. John Cole from Etri. So can you just comment a little bit on the future work that you mentioned about the wearing out part of the 3D printer issues? Yeah, mostly that's kind of the direction I would like to hear.
So 3D printers can actually manufacture a number of different types of materials. So there are printers that can do metal and these kinds of things. But the more important thing about this work is that we have a link between a digital model and a physically fabricated model, which is why we did those tests with the sort of laser cut materials that don't wear out along boundaries, since they're a uniform material. So we want to experiment with additional ways of fabricating the tines, but as long as we have that digital physical link, the technique will still work.
Because my concern was if you limit the types of fabrication material, you're going to have a limited number of frequencies that you can support, and you're just limited by the material right there.
Yes, it is definitely true that you're limited by the material. So I actually have some slides that I can show you. We experimented with a few different kinds of ways to sort of put the tines together. So you can do sort of a linear thing, but you can also interleave them. So in this way, you need more recognitions in a row to figure out where you are in the sequence, but you can, you can do it with fewer different frequencies. So.
Thank you. Great talk.
Thank you.
Okay, maybe while the next speaker comes and sets up, can you talk a little bit about the signal propagation through the rest of the printed object?
So we didn't experiment with it explicitly, except that we did do some tests where we had, sorry, I'll come over here, where we had basically 2 microphones clipped to either end of our input devices. And the thing is that both microphones had roughly the same recognition rate, although tines closer to a microphone are more readily recognized by it. So there is definitely some acoustic issues that we need to look into also in future work.